This is Lab 2, Motion of a Falling Object, by me, Adil Abdu. In this lab, we will be analyzing the motion of an object which experiences the force of gravity as well as drag force. In this case, it's a piece of crumpled paper. We will then compare the dissimilarities in motion that occur as a result of the drag force and see how it affects the final motions of the object. Physics topics seen are Newton's second law and the idea of air resistance. Newton's second law states that the net force of an object is seen as m equals ma, or F. Other fundamental physics topics as continued are the position update formula, as seen here, velocity update formula, Newton's second law in other terms, and the formula for air resistance. For position update formula, we have R final equals R initial plus V average times delta t. We use this to find and see how we use this to see how the position of the object changes over time and how air resistance affects the position change over time. Velocity update formula is almost the same. V final equals V initial plus F net over m times delta t. We also use this to see when the terminal velocity is reached and how the terminal velocity affects the motion of the object. F net is equal to delta p over delta t shows that change in momentum of an object is equal change in momentum of an object over change in time is equal to the net force of an object. Lastly, for F air equals k v squared shows that k, the drag coefficient, times v squared equals the force of air resistance. The software used to track the motion of the object in real time was the software called Tracker. As we can see here, the object, or system that I used, is this crumpled up piece of paper at the top of the screen. It then fell the full length of the meter stick downwards, and we can see that these data points plotted are here on the graphs on the right. This graph showing the y position over time, and this graph showing the y velocity over time. These data points were then put in this table, which can then be exported into an Excel spreadsheet to compare with the data from GlowScope. The software used here was GlowScope, which we could then use to visualize the expected data if there was no drag force. These inputs were used only with the net force acting on the object being the acceleration due to gravity and no drag force, which is not what's seen in real life. This GlowScope code shows what goes into the model that was used in the previous slide. We can see here that the net force is the only thing that's taken into account of, with the net force being only the force of gravity and no drag force. GlowScope can also be used to model what it would look like if there was drag force applied. We can see here that in the position versus time graph that the slope is almost constant towards the end of it, and that also on the velocity versus time graph, it almost hits a horizontal asymptote as we see this is the terminal velocity of the object or piece of paper that has been reached. Here we can see the GlowScope code used for when the net force would involve the gravity as well as drag force. We can see here that the coefficient b up at the top represents the drag force coefficient, and it's involved in the calculations used. I'm unable to get the graph into this PowerPoint, but what I can tell you is that the drag force, or because of the effects of the drag force, the final velocity is less than what would be expected of what actual velocity is. This is because terminal velocity is reached and drag force is acting in the opposite direction of gravity, which causes final velocity to be less or closer to the zero than what it is expected. So, what does it mean? When asked which models predict a terminal velocity, we can see that the model taken from the GlowScope with the drag force involved shows a terminal velocity. Looking back at that graph, we can see that at a certain point, it almost reached a horizontal asymptote. This is described as terminal velocity, when the air resistance of an object is equal to the force of gravity. For the what-if question, we're asked to imagine what if the object was originally thrown downward, what the terminal velocity would be, and if it would be different. So, as we can see here, I changed the terminal velocity in this case in the GlowScope code to -1. So we can see initial velocity here is -1. However, we see velocity as a function of time still reaches a horizontal asymptote as we see that terminal velocity does not change from before. This is because that no matter what initial velocity is, terminal velocity will still be the same for the object.